My name is Charles. Today I'm going to be making the case for language understanding in large language models, and a large part of this talk is based on joint work with my wonderful advisor, Martin Reinert. So anyone who's spent even a little bit of time with ChatGPT has probably seen it give outputs which make it seem like it actually understands what's happening. On the other hand, we have basically no visibility into how these language models operate, and it's entirely possible that such behavior is entirely attributable to just the massive scale of the amount of data going into these things, how long you train them for, and the number of parameters. So today, I'm going to be talking a bit about our research that is designed to give us insights into what's really going on inside language models, and whether they do, in fact, develop some understanding of reality. So this is Carol. We designed a series of controlled experiments using Carol. Carol is a nice little robot. You can control Carol using these commands. And this is what a Carol program looks like. So Carol is going to follow my lead: move, turn right, move, turn left. With this language, we can now define Carol tasks. And this is sort of actually borrowed from like an introductory programming language course. And so what you would do is you would say, OK, I'm going to give you a start world state. I'm going to give you an ending world state. And I want to know, can you give me a program that, when executed, will actually get me from the start to the end? So we can train a language model on this. We're going to basically give it a bunch of examples of Carol tasks, and then just train it using sort of standard pre-training. That's nothing fancy happening there. And then we can ask, does the language model learn how to write Carol programs? Right? I'm going to give it a completely new Carol task that it's never seen before. I'm going to have it generate text, and I'm going to see, does the program, when executed, map the input to the output? And of course, the answer is yes. I think anyone, no surprise here, the talk would have been over if the answer was no. It's kind of surprising how well it does, though. It gets to 92% accuracy, which is, it's an A. And the question, of course, though, is how? How is it doing this? Because even though I've sort of depicted Carol here in this very human-readable format, right? You can see the grid. You immediately intuit that the robot is facing the direction of the arrow. Everyone knows in this room, I hope, what move and turn right refer to. The language model sees this. The language model sees this pile of tokens that has absolutely no meaning to it whatsoever at the beginning of training. And I think if I put any one of you in a room and I gave you a pile of tokens and I said, figure out what this means, you'd have a really hard time realizing that there's like this robot Carol running around. So that's the question. The question is, the language model is only trained to predict the next token. It has absolutely no information about the domain, has no information about the task. It doesn't know that there's a robot running around. And yet, it appears to produce meaningful output by the end of training. And so the question is, does the language model have any understanding of what's going on? So what is going on here? Well, the language model is writing a program. As it does so, it sort of proceeds through its own internal states. And each internal state is just a giant vector of numbers. Each vector of numbers gives a single token. And here it's a program token. So the first vector of numbers says, I'm going to generate move. The next pile of numbers says, I think the next token should be turn right. But unknown to the language model, Carol is actually listening in. Right? Carol sees the language model say move, and Carol takes a step forward. Carol sees the language model say turn right, and Carol turns right. And the key part of this is that the language model has never seen these intermediate states. The language model doesn't know that Carol is listening in. All it knows is that there's this first state, this last state, and then this sequence of tokens. So does it know the existence of these intermediate world states that the robot traverses through when going from the start to the end? To answer this question, we're going to borrow a technique that's inspired by neuroscientists. Essentially, we're going to train these probes. Probes are intended to sort of go down into the inside of the language model and hopefully try to read some property of interest out of the state of the language model. And just for simplicity, I'm going to focus on the direction the robot is facing. And the idea of probing here is, if the language model knew what direction the robot was facing, if it actually knew that there is a sequence of intermediate states, I should be able to find some encoding of that in the internal state of the language model itself. And so the way we're going to do this is we're just going to train, the probe is just a classifier, right? So we give it the internal state of the language model as the input. Again, it's just a giant vector. And we're going to train it to predict what direction the robot is facing. And again, if the language model knows what direction the robot's actually facing, then this probe should be highly accurate. So here are the results. We trained the probe at regular intervals during the language model's training process. and then we plot how accurate the probe is at predicting the direction of the robot. And you can see here, so that's in green. We also plotted in orange the number of unique programs the language model writes down. And the reason this will become interesting is on the next slide. But essentially, there's 10,000 of these Carol tasks. And I'm just counting, of the 10,000 tasks, the language model gave one program for each. How many unique programs are there? So there's some pretty interesting trends here already. And in particular, we sort of isolated 3 distinct phases of learning. The first phase we call babbling, because it's characterized by this very low number of unique programs that are formed from extremely repetitive, meaningless text. And so the language model basically has no idea what it's doing. It doesn't even give you programs necessarily. It's just saying, like, put marker, put marker, put marker. And as a result, the robot's movements are also extremely limited and predictable, so the probe's quite happy at this point, right? It's saying, OK, well, it's not moving much. I think I can figure out what's going on. The second phase is where things get interesting, because you have a very sharp increase in the output diversity, but the programs aren't actually correct yet. And so what this sort of suggests is language model is learning how to produce program-like text. It's not actually programs, because they don't execute correctly, but looks something like programs. And here, as a result, the hidden states of the robot are very complicated, because it's doing all sorts of random things, and the language model has no idea what's going on either. So the probe, you can see it's like quite struggling. Now, finally, the language model gets to the point where it's able to give us correct programs. And now the probe is also able to basically pick up the direction of the robot. And what we'd like to claim at this point is the accuracy of the probe is evidence that the language model actually learns to track the movement of the robot, despite never having seen these intermediate states before. Of course, there is a possible alternative that we have to consider. And if you are scientifically minded or do a lot of empirical science, maybe you've already noticed it. But basically, the claim was in the back half of training, the high probe accuracy suggests that the language model knows the robot direction. Unfortunately, we can't actually draw this conclusion because the probe's accuracy is also high early in training for a completely different reason. And in fact, the language model doesn't know anything whatsoever. So how do we reconcile these two things? Now, this is actually a symptom of a more general problem when you're using supervised probes. There's just always these two competing hypotheses. So on the left, we have the outcome that we actually wanted, where the language model knows the direction of the robot. The probe sort of just goes in and reads that out. On the right, we have this competing hypothesis, which is language model has no idea what's going on about robots. It's like, what is a robot? But it does see the tokens that it's been generating. And the probe, we're saying, go in there and figure out what's happening. And it's like, OK, I can see the program. I can see where the robot was. I'm just going to execute the program myself. Right? You don't know what's going on, but I can still do it. And so the key is that because we're training the probe to actually do the thing, we can't stop it from doing hypothesis 2, even when what we actually want it to do is just hypothesis 1. So how are we going to disambiguate these two competing hypotheses? We designed another controlled experiment. The intuition here is, look, if the probe is the one doing the task, if the probe is figuring things out on its own, let's just have it figure out something else, right? Because it should be able to do that just as well. So what we're going to do concretely is we're going to fix the language model now. That thing's not changing anymore. We're going to change the meaning of the commands for the probe only. So now every time the probe sees turn right, Carol is actually going to turn left. Sorry, when it sees move, it's actually going to turn left. And when the probe sees turn right, Carol is actually going to take a step forward. And the key is that the probe should be able to do this equally well, right? We're going to train a new probe that's going to go from the original language model internals and try to predict these altered states. So this is what that looks like. And the reason it's going to help us tell these two hypotheses apart is because on the left now, we have the world that we want it to be in, right? The language model knows the direction of the robot. And now we're asking the probe, hey, can you go from this original direction to this altered direction? And the probe is going to say, well, that's not there. I don't know what you're asking me to do. On the right, we have the hypothesis that we want to exclude or reject, which is that the probe is able to actually learn how to execute programs. And so when we ask the probe to do something new, the probe doesn't know English. It doesn't care that you showed it move, but the robot actually turned right. It should be able to do this all just as well. So what is it? Turns out the probe can't extract altered states. This is consistent with our initial hypothesis. And you can actually notice a bit more detail in the plots as well. Interestingly, during the babbling phase, the language model states are in fact meaningless, and this is sort of evidenced by the fact that you can't actually distinguish the two hypotheses. So the probe is in fact learning to do things itself. As soon as the language model starts to latch onto sort of the semantics of the programming language, and it starts to know sort of how to give you correct programs, however, you can start to distinguish the two probes, right? You can't map to the altered states, and the probe is actually sort of tracking what the language model knows. So I want to take a step back now and sort of discuss maybe some of the broader implications of these findings. Because essentially what we're saying here is that even though the language model never saw any intermediate states, it never was given any information about robots, the fact that there are sort of steps happening alongside the program, by the end of training, and correlated with the ability of the language model to actually generate correct programs, the language model has developed some internal model of the robot's path. And we're actually not alone here. Many others before and after us have found similar evidence that textually trained language models can actually access some model of reality. And what I think is really exciting about this direction, this work, is that we actually now see a path where this emergent internal model of reality could possibly explain the ability of these language models to generate externally meaningful responses. And what's even more intriguing about this is that when you ask the language model to give you 10 things to do on a rainy day, despite the fact that language models could never possibly experience rain themselves, it's possible that the reason they give you 10 things that make sense to do on a rainy day is because they have some model of what it means for a day to be rainy that's consistent with reality. So I want to finish now by stating the case for language understanding in large language models. And when I say that, what I really mean is that I think we can and we should be building towards scalable, data-driven models of reality. I think the fact that language models are trained just on text now is a red herring. I think it's not the most efficient way to get there, but there's nothing fundamental about textual pre-training that prevents language models from inferring other things. And as we add more modalities, they will understand more and have more accurate models of reality. And I think the research that I presented here today highlights sort of the potential for language models to acquire better meaningful representations of the world, and suggests that these representations might be related to their ability to successfully complete complex tasks that would involve an understanding of reality. Thank you.